All right. Good morning. Welcome to my stream. And where were we? So, yeah, we finished the... Let me switch over. We finished the chapter on functions, right? Let's take a quick look at log. And, it's a little slow this morning. There we go. Native functions. So we got native functions working, which means we can say cargo run, and we can say print clock. As soon as it's done compiling, there we go. And it'll print out the time in milliseconds since January 1st, 1970 UTC, which is cool. But the next thing we need to work on is closures, and I mean, if you look at the scroll bar here, it's tiny, which means this thing is big. And this is a lot of code, or a lot of stuff we have to either learn or port or both, I guess. Wow, look at all this. Okay, so this is gonna and it's still going. Of course it is. And then we have a couple of challenges. And then a design note closing over the loop variable. Okay, so with that in mind, it's probably going to be the case that we don't finish this today. I would actually be surprised if we even got halfway today. So that's going to be the objective today, is to try to see how much closure we can get. Oops, I meant to do that over here. Okay, so what we have a bunch of different locks programs. And locks, star locks, right? We can say do cargo run, no default. Oh, actually, I can just build it. Cargo build no default features release. And we can see these programs all run for I and star.locks. Do, let's see, target release locks bytecode of I. Oh, right. One of them is that fib that takes forever. All right. So while that's running, actually, what I should do is do this so you can see each one. Echo I. I don't know why I'm putting them in quotes. Yeah, so it's running fib. Okay. So, closures. Thanks to our diligent labor in the last chapter, we have a virtual machine with working functions. What it lacks is closures. Aside from global variables, which are their own breed of animal, a function has no way to reference a variable declared outside its own body. Oh, we have a problem. We introduced a bug somewhere. cat4 test. This seems like a perfectly reasonable thing to do, but it looks like we have a bug we need to fix. But VM line 143. What's 143? Oh, yeah, we added this one business here. We have a functional problem, don't we? Because I think we added this one after we added functions, and this one here. Do we have a bug in? Let's try to make that a function. For test, for function test. If we make this a function, foo, right, and then call foo. Oops, come on. Wow. My hands. Okay, foo. Like that. Cargo run for func test. And that did not panic. Let's target release locks that. Yeah, okay, so in the function it works, and outside, let's just rerun it outside the function, it panics. All right, we should definitely fix that before we keep going and keep reading about closures, because there's no sense in doing closures if our code is broken. When we create a new function, I'm trying to remember because it's been a week and well, not a week, but last time I worked on this was Thursday, which is 1, 2, 3, 4 days ago. Let's see, it would be in the compiler code where we create a new function. Right. I think the idea is we don't want this here. So let's fix this. Let's fix the code such that we don't need this +1 business. Because we originally had it working without the +1. And I bet you if I take away this +1, the other code does work. The other for loop should work. So if I say, not this, cargo, run, for test. Yeah. Okay, so that fixes that. So let's get the functions working with this sort of code in the get local and set local. So where do we create a new function? fn function. Right, this is where we create it. All right, so we generate a previous compiler result new with the Lexium clone chunk type function. And then how do we create a compile result in the script? Because that's the difference, right? We have this compile result. We say compile result default. And then when we compile, what do? Oh, okay. We need to do this, don't we? When we create a new compile result, I think that's what's missing. We push this extra, right? This gets us a new index. So let's say default for, where's our default? Here it is, new. So we need to push this local. So I'm just pasting it here. We don't want this self result borrow push local. We want to create locals. Let's go up here and see what the compile result looks like, because I've forgotten. So it's a ref cell vec local. So we can create that, right? Let locals equals ref cell new. I guess we don't need two windows right next to each other. Ref cell new, vec new. And we can say locals dot borrow mut dot push of local. Right, and then just put locals in here. Is that the bug? Let's see if this builds. It builds. Okay, so let's see, can we run the for test? We can, and can we run the for func test? We can. Okay, so that was the bug. All right, so Clippy is happy, hopefully, and git at source, git commit fix stack index bug, I guess is what I'd call it. And now I say for I in that, it should just run them all. Okay. All right, back to normal. Bug fixed. Aside from global variables, which are our own breed of animal, a function has no way to reference a variable declared outside of its own body. Right, so we can grab this and... What? I thought I just fixed that. Oh, I didn't... I didn't rebuild the release. Alright, so we'll do that for test. Just double check. Okay. Let's run this. This will be our closure test. Copy, paste, and run this example now, and it prints global, and it's supposed to print outer. Cargo run closure. Well, let's actually run it here, so I don't see all the other output. Closure. It prints global, and it's supposed to print outer, right? Because X is referring to this X, not to this global X. And what's happening is we don't save any information about this local X. So since the only X that's in the inner scope is the global scope, the only X that's not in inner scope is global scope, that's what we print. That makes sense. To fix this, we need to include the entire lexical scope of all surrounding functions when resolving a variable. How hard is that? This problem is harder in CLOCKSS than it was in JLOCKSS because our bytecode VM stores locals on a stack. We used a stack because I claimed locals have stack semantics. Variables are discarded in the reverse order that they are created, but with closures that's only mostly true. Make closure has var local, creates a closure, prints local, and it returns this function. So this local should refer to this. So if I wish triple click worked on this. On Advent of Code it does. So let's call this make closure. Base. So what is this going to execute? End up running? Undefined variable local, right? Because it couldn't find local in the closure scope, so it looked in global scope instead of looking in the make closure scope. The outer function make closure declares a variable local. It also creates an inner function closure that captures that variable. Then make closure returns a reference to that function. We can actually run the locks ast release target release. And we should be able to see it run correctly. Yeah, it prints local there. And if we look at just the regular closure, it should print outer, right? And it does. Okay. This is how we can verify our thing is working. We could solve this problem dynamically allocating memory for all local variables. That's what JLOCKSS does by putting everything into those environment objects that float around in Java's heap. But we don't want to. Using a stack is really fast. Most local variables are not captured by closures and do not have stack semantics. It would suck to make all of those slower for the benefit of the rare local that is captured. There's a reason that C and Java use the stack for their local variables, after all. Right, because it's fast. Okay. This means a more complex approach than we used in our Java interpreter. Because some locals have very different lifetimes, we will have two implementation strategies. For locals that aren't used in closures, we'll keep them just as they are on the stack. When a local is captured by a closure, we'll adopt another solution that lifts them onto the heap where they can live as long as needed. All right. Closures have been around since the early Lisp days when bytes of memory and CPU cycles were more precious than emeralds. Over the intervening decades, hackers devised all manners of ways to compile closures to optimize runtime representations. Some are more efficient, but require a more complex compilation process than we could easily retrofit into CLOCKSS. Search for closure conversion or lambda lifting to start exploring. I'm just going to take a quick peek, but I'm not going to do anything about it. Ooh, there's a whole slide. All right, well, I'll take a look at that offline. Interesting. The technique I explain here comes from the design of the Lua VM. It's fast, parsimonious with memory. I think that means frugal. Stingy or frugal, okay. And implemented with relatively little code. Even more impressive, it fits naturally into the single pass compilers CLOCKSS and Lua both use. It's somewhat intricate though. It might take a while before all the pieces click together in your mind. That's a shame because that's going to make it porting harder, right? Because the idea behind porting is I'm taking the C code and I'm converting it over to Rust. But if the C code is going to deal with lifetimes and stuff like that, moving stuff from the stack to the heap, it's going to be a lot different. The Rust implementation is going to be a lot different to the way it's done in C. All right, we'll build them one step at a time, and I'll try to introduce the concepts of stages. Okay, fair enough. Closure objects. Mix a pick. Good to see you. How are you? Our VM represents functions at runtime using obj function. Okay, we're going to... Yes, that's true. We can take a quick look at that. We have this function here. Oh, and it's over here, right? We have the arity chunk and pub, and I made the chunk pub just to save all the headache of making a getter, which isn't much, but all right. These objects are created by the front end during compilation. At runtime, all the VM does is load the function object from a constant table and bind it to a name. There's no operation to create a function at runtime. Much like a string and number literals, there are constants instantiated purely at compile time. In other words, a function declaration in locks is a kind of literal, a piece of syntax that defines a constant value of a built-in type. Okay. That made sense because all the data that composes a function is known at compile time. The chunk of bytecode compiled from the function's body and the constants used in the body. Once we introduce closures, though, so the chunk of bytecode contains the constants. Let's take a quick look at that just to refresh our memory. It contains a code. For every byte of code, we record what line it was compiled from, and then we have the constants that are defined inside the chunk. And the function itself has the arity of how many arguments it takes. And we don't store the argument type because that's done dynamically at runtime, and then the name of the function. Right, once we introduce closures, though, that representation is no longer sufficient. Take a gander at this. This will be the baking closure. So if we run this using locks AST, we see donut and bagel, which makes sense because we're making a closure that returns the value that gets passed in. So this value gets captured from this argument, right? So we get donut and bagel. If we run this in our code, we have undefined variable value at line 3, called from line 10. Oh, there, called from line 10. Okay, the make closure function defines and returns a function. We call it twice and get 2 closures back. They are created by the same nested function declaration closure, but close over different values. I don't know who came up with the idea that it's closed, that makes sense to close over. Maybe that's something from math that I'm not familiar with. When we call the 2 closures, each prints a different string. That implies we need some runtime representation for a closure that captures the local variables surrounding the function as they exist when the function is declaration is executed, not just when it's compiled. We'll work our way up to capturing variables, but a good first step is defining the object representation. Our existing, and this is something, you say that, right? But this is something you need to know how it's going to implement before you can say, okay, here's what our data looks like. We're kind of going backwards because he's already figured out how to implement it. And now he's saying, okay, we're going to define the object representation based on how I'm about to implement things. So he's kind of cheating, but let's go with it. The Lua implementation refers to the raw function object containing the bytecode as a prototype, which is a great word to describe this, except that word also gets overloaded to refer to prototypal inheritance, which we talked about this in the JLox version. At runtime, when we execute a function declaration, we wrap the obj function in a new obj closure structure. The latter has a reference to the underlying bare function, along with the runtime state for the variables the function closes over. So the obj closure is going to have a function and then captured variables go here. All right, so I guess we could start writing our first bit of code. We actually have, so if we look at function here, this is the function definition. We now going to have a closure, which is going to have a function in it. I guess maybe this should also go in its own file, separate from value. Right. Here's what I'm thinking. We'd have a closure, RC closure, right? And then the closure will have the function, and then we're going to add stuff to it. But it'll just start out as a function, which is going to be pretty straightforward because it's just going to be use create function star and then just pub struct closure function. I guess this is an RC, right? That's what we want. Which means we need to use standard RC. And that doesn't compile because closure is not found in the scope. Okay, and that doesn't compile because could not find closure because I didn't put it in main. And now this doesn't compile because closure doesn't implement the bug. Okay. And this doesn't compile because now we have to deal with cloning and stuff. Okay, so this is pretty straightforward. Value closure C, value closure RC clone OC. And then we need display. Ooh, how do you display it? I guess we haven't even peeked ahead that far. But I'll just put a closure there just to get this to compile. Right. F. I guess we could say, well, we can change it when we need to, and this will just be closure.function.name. Oh, yeah, I'm just using the display property of that, right? I don't know if that'll work. Right, bang. Yeah, it's a private field. I'm trying to see, this extracts the func there. Let's take a look at function. And how do you just issue a display on it? That's all I'm trying to do. I don't want to call .fmt. That doesn't make sense. Oh, it's a private field. I guess what I can just do is implement display for closure, right? Which is just going to be the same thing as all this. Except I put the word closure here. And then I can just say closure. And then down here, we don't want to say this name is empty. We want to say self function format. Maybe? No. Oh, I have to import that. F. Okay, this is kind of weird. I don't like having to call like that, but I don't know of a different way to do it. All right. I think the only warnings are that we're not using it, right? Or we're not using formatter there. Okay. I don't have closure in the Git files. What? I must have a key thing for VMRC. I have a key code for Git files, right? Or G files. I have a key code for just regular files, right? And then I can go closure, right? I should need I should add a okay, so let's go to here, oops, and remove the formatter. Okay, so now the only thing is we're not using closure. Okay, so we have a closure now. There's nothing in it yet, but we're going to add local variables. Captured variables go here. I'm just using this line here. All right. So this is where where we want to start. We'll wrap every function in an object closure, even if the function doesn't actually close over and capture any surrounding local variables. This is a little wasteful, but it simplifies the VM because we can always assume that the function we're calling is an object closure. Oh, so that means if I look at value, what we're saying is we're going to get rid of this and just use closures from now on. And if the function is not a closure, well, we'll stick it in the closure object and just call it, but not worry about local variables or captured variables. So this is going to mean some refactoring. This is the new struct. Right now it simply points to an object function and adds the necessary object header stuff, grinding through the usual ceremony for adding a new object type to clocks. Right. So we have new closure, which we don't have to implement. Actually, is there a in function? Is there a new in function? There is. So this would be something that closure new would have to. Oh, this is a new closure function. Okay. So is that the way we want to do it? Let's do it down here so I can see. So if I say impl closure, pub fun new, and it's going to take a function, right? And it's going to return self. We'll just say self function rc clone function. It doesn't like that. 12 errors. What did I do wrong? Oh yeah, now I commented out this from value. That's what the other errors are. So we have to now work our way through all of this and make, instead of value func, we have to make value closures. Right? It takes a pointer to the object function it wraps. It also initializes the type field to a new type of closure. Okay, so we still want function values. Interesting, right? We still need those because the closure has to refer to them. Or does it? We free the only the object closure, not the object function. That's because the closure doesn't even own the function, right? That's why it's an RC inside. Okay. There may be multiple closures that all reference the same function, and none of them claims any special privilege over it. We can't free the object function until all objects referencing it are gone, including even the surrounding function whose constant table contains it. Tracking that sounds tricky, and it is. That's why we'll write a garbage collector soon to manage it for us, which I don't have to do in Rust. Perhaps I should have defined a macro to make it easier to generate these macros. Maybe that would be a little too meta. These are the macros that we get out of the enum capabilities of Rust, so we don't need to write those. Closures are first-class objects, so you can print them, right? So I already wrote the display for it. All right. They display exactly as object function does from the user's perspective. The difference between object function and object closure is purely a hidden implementation detail. With that out of the way, we have a working but empty representation for closures. All right. But all the places we use value : func. Let's see. Just look for func. I guess I have to search for, I have to search for func. Like that. Oh, this is only one spot here. Okay, then VM must have the remaining, yeah. So we must be pushing, instead of a function, we're going to be pushing a closure. And when we get the chunk, we're going to have to get it out of the closure instead of the function. All right, So we're going to have to figure that out. We have closure objects, but our VM never creates them. The next step is getting the compiler to emit instructions to tell the runtime when to create a new object closure to wrap a given object function. This happens right at the end of a function declaration. We're going to create a new opcode called opclosure. So right now we emit bytes constant. So instead of that, we're going to be replacing it with opclosure. And we're going to call obval function. So we're putting a function on there, but calling it a closure. Does that make sense? Or should this change to closure as well? I forget what obval does. But this is a function, right? So we're returning a function and then we're saying, oh, this is a closure, by the way. Is that going to change? Because that seems broken to me. Here's interpreting as function. New closure. Oh, this is executing the thing. Okay, so we are pulling a function as the constant. We're not making a So how do we know? Okay, I guess opclosure then points to a function, not to a closure. Okay, so we'll just do that. Closure. We have to add it to the chunk. Yeah, this is definitely going a lot slower than, and we have to add it to our opcode table. So this is opcode 25, opcode, closure. And then in disassemble instruction, we have, oh, we're putting this directly in line, huh? Okay. Opcode, closure. Instead of calling self closure instruction, we're just doing this. I'm not going to increment offset because offset gets passed into here and it's not mutable. But we're going to just return the amount. So let's just, I guess we can say let mut index equals offset +1. There's the first line there. You can say let constant is equal to chunk of code offset. So this would be self.code offset, and we're going to increment it again. Oh, not index. And we're going to say index plus equals 1. That's this plus plus here. Then print bang -16. Let's see, how do we do this? -16 and then the constant 4. Opclosure. Print value. How do we do print value? Okay, self constants, print value. Constant is usize, and then println like that, and then we're going to return index. Oh, colon -16. Opcode. Okay. And closure is not covered in the VM. Okay, so we're going to get to that. There's more going on here than we usually have in the disassembler. By the end of the chapter, you'll discover that opclosure is quite an unusual instruction. It's straightforward right now, just a single byte operand, but we'll be adding to it. This code here anticipates that future. Okay. Most of the work we need to do is in the runtime. We have to handle the new instruction naturally, but we also need to touch every piece of code in the VM that works with object function and change it to use object closure instead. Function calls frames. We'll start with the instruction now. Okay, good. Opcode closure. So we're going to take the function from this. So we must have another place where we do a read constant. Yeah, right here. So we can grab that. And then we grab the closure and we create the new closure right there. So we're going to say let closure is equal to value. Oh, well, we can just create the closure, right? So closure new. And we want to read the function. Let function is equal to Oh, this does come out as a function, right? So say let constant, and then we can say if let value function equals constant, right? That's how we extract it. Then we're going to say let closure new function, because this is the RC that's coming out of here, and now we have a new closure. And then we're going to self.push, self-stack push, value closure. And then we're done. Else panic. Tried to read function. Constant table, but got constant. Can I do debug output in a panic? Let's find out. Closure does not exist. Closure is still having a problem. Expected RC found struct closure. Oh, RC new? Yeah. Okay. So that's there. We're still not creating them. So we got to get to that part. And once you have a closure, you'll eventually want to call it. So in call value, we're going to replace two lines. So we're never going to call a function. We're only going to okay. So if we have a closure, we're going to call, which is going to look at the top of the stack again. Which unfortunately means this callee arity business has to pass it down to the function. Right? We're just going to add a reflector for this. Arity self resize self function arity. And then what else are we going to need for this guy? Oh, that's it. We are passing in that's going to be a problem too, right? Because what we're doing is we're pointing the function pointer here onto the stack that has the closure, and it no longer has the function. It now has a closure. So that means this is not a value func, it's a value closure. See? And now get chunk needs to be passed along. Pub fun. Oops. What does get chunk look like? There aren't too many. There is top level, stack name. Self function, get chunk. Let's see what else blows up. Oh, we don't have chunk. Okay, so that one got translated, I hope correctly. I don't know what else I broke, assuming that the function is on the stack. I guess any place we need current frame. Any place we use current frame, we could potentially get the function and use it. So where else are we doing that? That's the IP. I guess that doesn't matter. Slots. What is a slot? That's just an array of view size. Okay. That doesn't have to change. That's ink, ink, ink. And then we're back. Okay, so I think we're okay. Although, why is this doing this here? Why don't we do this? We can just say self current frame. All right. Does this still run, by the way? Let's build release. And for I in all of these things, are these? No, of course not. Tried to call a non-function, line 218. So let's fix that. Oh, so what is on there? Self peak arg count. Is there a function on the stack instead of a closure? Let's just run one. Cargo run. Bake. Okay, so. Yeah, so it's got a function on the stack. So what is it running here? It's function. Oops, I forgot a space. Make closure. Defines a global. Gets a global. So it goes on the stack. It puts donut on the stack and then call. So it should have been calling. Oh wait. Wait. This is the script, right? I can't see in here. I see a whole bunch of stuff, but I was looking for the function name. Name is empty. Here it is. So that means that top level script needs to be adjusted. Okay, maybe we're going to get there. Maybe I'm jumping the gun. So that's that. When we call, replace one line. Oh, take the closure instead. But right now we're just looking on the stack to get the closure, so we don't pass it in. In the body, we need to fix everything that references the function to handle the fact that we've introduced a layer of indirection. We start with the arity checking. Okay, so I added that in closure itself. Right, this is the layer of indirection to get the function's arity. Right. The only change is that we unwrap the closure to get the underlying function. Next thing call does is create a new call frame. We change that code to store the closure in the call frame and get the bytecode pointer for the closure's function. I'm doing that. This necessitates changing the declaration of call frame 2. I don't need to because I'm looking directly in the stack, which might bite me later, but let's find out. Every piece in the VM that accesses call frame's function needs to use the closure instead. We're doing that. Here's disassemble when debug. Trace execution is enabled. It needs to get the chunk from the closure. I'm doing that here. Likewise, when reporting a runtime error. Oh, runtime error. Let's take a look down there. That's down here. We're still using get chunk here, so that's okay. Because this function is, oh, Yeah, so the function here, this should be the closure. Right, and then we say closure get chunk. Okay, so that fixes that. Almost there. The last piece is the blob of code that sets up the very first call for. Right. So this is the thing we hit with our panic. So fn interpret, replace one line. So instead of pushing a function, we're going to push a closure, and it's going to be an RC new of closure new function. So now we have this extra layer of indirection, and this has to be closure. And RC new. Wow, we got double RCs. Very good. And this still. Oh, we have to add stack name. Okay. Source closure. Pub fun stack name. Self. I don't know what it returns. Self function stack name. Compiler's about to tell me that I got it right. Okay, just out of curiosity, it is a string. Okay, so now will this run? Whoo! Look at that. It still doesn't work because we haven't gotten. We're not capturing values anymore. Sorry, not capturing values yet. But at least it's not panicking. All right, so I'm going to mark that as 25.1. Git status, git add source, git commit, section 25.1, and it was called closure objects. Okay. So for 25.2, up values. Okay, the compiler still returns a raw object function when compiling a script. That's fine, but it means we need to wrap it in object closure here before the VM can execute it. Right. The code looks a little silly because we still push the original object function onto the stack, and we pop it after creating the closure only to then push the closure. Why put the object function there at all? As usual, when you see weird stack stuff going on, it's to keep the forthcoming garbage collector aware of some heap allocated objects. Right. So I didn't do that because we're not writing a garbage collector. We're back to a working interpreter. The user can't tell any difference, but the compiler now generates code telling the VM to create a closure for each function declaration. Every time the VM executes a function declaration, it wraps the object function in a new object closure. The rest of the VM now handles those object closures floating around. That's the boring stuff out of the way. Now we're ready to make those closures actually do something. All right, so let me compile release. Let me run that for loop. Make sure they're all still working. Or at least I want to see no panicking. And we can look at up values. Our existing instructions for reading and writing local variables, yep, okay, good, are limited to a single functions stack window. Locals from our surrounding function are outside of the inners functions window. We're going to need some new instructions. The easiest approach might be an instruction that takes a relative stack slot offset that can reach before the current function's window. That would work if closed over variables were always on the stack. But as we saw earlier, these variables sometimes outlive the function where they are declared. That means they won't always be on the stack. The next easiest approach then would be to take any local variable that gets closed over and have it always live in the heap. When the local variable declaration in the surrounding function is executed, the VM would allocate memory for it dynamically. That way it could live as long as needed. This would be a fine approach if CLOX didn't have a single pass compiler, but that restriction we chose in our implementation makes things harder. Take a look at this example. Here the compiler compiles a declaration of X at 1, emits code for the assignment at 2. It does that before reaching the declaration of inner at 3. And discovering that X is in fact closed over. We don't have an easy way to go back and fix that already emitted code to treat X specially. Instead, we want a solution that allows the closed over variable to live on the stack exactly like a normal local variable until the point that it's closed over. Fortunately, thanks to the Lua dev team, we have a solution. We use a level of indirection that they call an up value. An up value refers to a local variable in an enclosing function. Every closure maintains an array of up values, one for each surrounding local variable that the closure uses. The up value points back into the stack to where the variable it captured lives. When the closure needs to access a closed over variable, it goes through the corresponding up value to reach it. I'm not sure I'm quite following yet. When a function declaration is first executed and we create a closure for it, the VM creates the array of up values and wires them up to capture the surrounding local variables that the closure needs. For example, if we throw this program at CLOX, the compiler and runtime will conspire together to build up a set of objects in memory like this. So we have the function, which has an up value array. We have entry 0, which has a location pointing to here. The closure itself has the function, which has the chunk and the constants and line numbers. That might look overwhelming, but fear not, we'll work our way through it. So I guess what we're doing is we're just creating for up values, we're creating a vec, and then we're going to just have an address on the stack to look at. I mean, in Rust, maybe that's the easiest thing we have, right? This is the index of the up value, 0 through n, and then just a U size into the VM's stack. We can try implementing it that way and see how it goes. That might look overwhelming, but fear not, we'll work our way through it. The important part is that up values serve as a layer of indirection needed to continue to find a captured local variable even if effort moves off the stack. Oh, if it's moving off the stack, excuse me. If it's moving off the stack, then we can't just have an index into the stack to refer to it. How does it move off the stack? Before we get to all that, let's focus on compiling captured variables. I'm trying to think about, again, this is the advantage he has is he's already written this thing and now he's describing how it's written rather than working the way through it. What is this going to do? All right, well, I mean, what we can do is just barrel on, and then we might have to do a massive refactoring job in order to handle this, because in C, you can just stick a pointer here, right? And then if this moves off the stack, you can just update where this is pointing. I don't know if that's what they're going to do in the book, but that's what I'm thinking, that would be the easiest thing to do, is if this thing moves off the stack, we could just have an A in memory somewhere that this location points to. And in Rust, if this is a U size, you're not going to be able to do that. We need like a box or an RC for it. As usual, we want to do as much work as possible during compilation to keep execution simple and fast. Since local variables are lexically scoped in logs, we have enough knowledge at compile time to resolve which surrounding local variables a function accesses and where those functions are where those locals are declared. That in turn means we know how many up values a closure needs, which variables they capture, and which stack slots contain those variables in the declaring function's stack window. Currently, when the compiler resolves an identifier, it walks the block scopes of the current function from the innermost to the outermost. If we don't find the variable in the function, we assume the variable must be global. We don't consider local scopes of the enclosing functions. They get skipped right over. First change then is inserting a resolution set for those outer local scopes. And then we're going to call resolve up value. This new resolve up value function looks for a local variable declared in any of the surrounding functions. If it finds one, it returns an up value index for that variable. We'll get into what that means later. Otherwise, it returns -1 to indicate the variable wasn't found. In Rust, we will use an option. If it was found, we use these two new instructions for reading or writing the variable through its up value. All right, so one of the things that I did, and I can see already is an issue in the compiler, when it's a function, what I did was I just pushed the previous compiler onto a stack and replaced it with the compile result of a function type. And then when we were done compiling the function, I just put it back. Now I can see that we actually need access to it to call resolve up value and resolve local, which means we're going to have to refactor a bunch of stuff. Let's add these things in. I'm just scanning forward to see where they're actually being used, because adding them in means we have to modify. Wow, we're not even using them for a while, huh? Let me scan back up here. Op get up value. And where is that? It's right here. Here. This is referring to it there, and then all the way down here is where we actually start implementing it. And they're byte instructions. All right, so yeah, let's throw it into the chunk code. Get up value and set up value. We can add those here. Up value, and then in our disassembler, opcode get up value, self byte instruction, op get up value, offset, and it becomes an S, and that becomes an S. Okay, so that was easy enough, and now in our VM it's going to blow up, right? Because we don't have a, yeah. So opcode get up value, or opcode set up value to do. Okay. All right, so we got that part working. Let's go back to now where they're defining. Sorry, we got this compiling. All right, so we're going to have to refactor some stuff here, because if we're going to work our way up to the resolve locals, let's take a look at what resolve local does. Compiler. It's right here. So we're going to look at the self result borrow find variable. Where's that? Oh, that's inside our compile result. Okay, so if I look, where is this called? It's called the name. Oh, that's the only place it's called. Okay. So should we actually should we lift resolve local? I think we should. I think we need to lift resolve local into compile result. Let's copy it there and see what needs to modify to get that to work. Because that way I can stick the enclosing thing here. This is what I'm thinking, right? Because we have the compile result, we have to have an enclosing, which is going to be a RC2 compile result. No, RC2 option. No, an option. And are we going to have to modify it? If so, then I'll have to throw it in a ref cell. Right. And this defaults to none, which makes sense. But when we create a new one, we're going to need a reference to the current one, so we can put it in here. All right, so I'm going to leave that alone for now, and then let's see. Here's find variable. Let's put in. Oops. Nope. There it is. Here's resolve local. So instead of saying self result borrow find variable, we'll just say self find variable. And then let's look at the find local here, and this will just say match self result borrow find local. Oh, we can just return it, right? Find local name. And that'll return an option U8. Ooh, so this also has to be a result, right? Because we need to be able to report this error. Find result. Okay, so all this does then is find variable. So why am I moving this up? I need to move it up because it needs to be in here. This resolve local becomes what? All this has to translate to the option U8. Okay. So why can't this call yeah. Programmer says, what's the color scheme you're using? I am using whatever ToggleBit set up. I will paste a link to his thing. It's called Toggle Colors or something for his own colors. This is it. This file right here. And I'm sure there's some Rust stuff in there too. I don't know. Yeah, it's pretty nice. I mean, it's high contrast, which is why I like it. So I'm trying to think, do I even need this? I do need to be able to do a resolve local here, but maybe named variable can just ignore all of that, right? Maybe named variable can just call results resolve local directly. Except the fact that we need to be able to report, we can't read local variable in its own initializer. So we still need to be able to do that. But we need to be able to pop up a level in the enclosing code. Okay, so we just need to rejigger this. I think let's for now just say match on this guy here and work it that way. And then this is just a interface into this find variable. And it might be we can just eliminate it at some point. Or resolve local might get more complicated. Expected results. Oh, I probably need to. No, this is doing the result thing. Oh, this is returning find. Oh, okay. Yeah, we need to translate it. Okay, so we just need to do this. And then say this is error. Oh. Match this. Find result uninitialized is a none. Oh no, is it? It's it, right? Not found becomes none. Okay, none. Yeah, so we just need uninitialized, and then the other two just become okays. So this becomes error this, that, and then okay, result becomes result. Right? Okay, that works. So we can just say error find result on initial. I don't know how to type that. Find result not found becomes okay none, and find result depth D becomes okay sum D. And then we get rid of these lines. There. Let's see what blows up now. Forgot that. Oh, there. Oh, what am I doing? This should be okay. Val, and it just becomes val. And this is result, borrow, find local, resolve local. Patterns error not found, an error. Oh, we'll never get those though. Panic. Invalid return from resolve local. There. Okay. And now the warnings are we're still not using closure. Oh, we're not using enclosing. Unreachable pattern. Oops. Line 219 in chunk. Oh, right, because it has to be 27. Okay, glad I checked. Okay, so we're not using this enclosing, and now that's what we need to do now. We have to go over to the compiler, and in fn function, we need to pass in the previous compiler, the enclosing for the previous compiler. Ooh. So I do think we need to make this a ref cell. Because I need to replace it if it's not a... Ooh. What it'll do for default for that? It comes up with the default. Hopefully it's a ref cell to none. Right, the optional... Right, okay, so hopefully that works. And then we can say here self results dot enclosing dot replace with prev compiler or sum. All right, so that puts the prev compiler in here. And then before we pull it out, we need to put in a none. You can say let prev compiler. This is a little awkward, isn't it? Self result enclosing replace. Oh, that's probably a borrow, right? This is equals. Programmer says I tried using it, I just can't set it up. Are you talking about the whole thing that Togglebit set up, or are you talking about, oops, this thing here? This has the setup instructions for this, but you can just copy the colors over. I don't know how to reference this colors file. Oh, it's probably in, yeah, color scheme Togglebit. So you just copy the colors file into the colors subdirectory under config, right? Let's take a quick look. Yeah, so you put the color file in here, and then in your vimrc, you just say color scheme Togglebit, and that should do it. Okay, where was I? Replace with, oh, we're going to just extract it, so none. Right? We're pulling it out, and this I need to enclosing borrow replace. No, result borrow, enclosing replace. All right, let's see what blows up. Doesn't like this because it's expecting RC, and it found a compile result and wanted an RC compile result. Is that going to blow things up? Or maybe I pulled the RC out. Maybe we don't need this to be an RC. I don't know. I don't know if that'll work. Recursive. Oh yeah, it does have to be an RC because otherwise it's recursive. Yeah, if you're a programmer, if you're not using NeoVim, I don't know how to help you otherwise. Sorry. Okay, so if we leave this in RC and then we have to make this in RC, but that means when we extract it here, and put it in here, that's going to be a problem because now this is going to be an RC. Yeah, expected compile result, found option. Oh, we can unwrap it. Now it's going to say, oops, it's going to say found an RC. Yeah, that's a problem. Can we throw an RC into here without any pain? Just a little bit of pain. Expected. Oh, because I'm doing an extra here. Okay. Ooh, okay. So we got that to work, or at least compile. Now the question is, can we use it to work our way up? Right, so we're looking at this. The reason we were doing that is so we could do this, resolve up value. So let's say resolve local. Let's write a resolve up value. It's going to also return a result of an option U8 and a find result, I assume. Oops, I didn't add that, so now that doesn't work. Okay. So the first thing we're going to do is say if we don't have an enclosing, then we're going to return -1. So that's going to be find result not found. Mistyped up value. But, okay, so who's calling this? We're calling it here. So we need to have the same kind of semantics as resolve local. Right, okay, so it's returning this. That's fine. So if self dot enclosing dot borrow is none, right? If there's no enclosing, then we're going to return okay none. Didn't find anything. Otherwise, we're going to recall self resolve local. On the enclosing, borrow, resolve, local name. And that's going to give us a result. And we can question mark that, because if it returns an error, we can just throw that, saying it's uninitialized. Or do we just say, okay, -1 here means it's not found. And then we call this function called add up value, which doesn't exist yet. I'm passing in true. If local is not equal to -1, in other words, we got okay, some d, some depth. So that's what we're going to see out of this. So I can say question mark here and then unwrap. Oh, not if it's a none. Okay, so maybe we do a match, right? If it's okay none, we don't do anything. If it's okay some depth, right, that's this line here, then we're going to return, we could just say return okay none. Otherwise we're going to return self add up value, whatever that does, on the current state, right? The local, which is depth, and true, whatever that means. Why are we passing in true? And we need to add up value. Oop, this needs an arrow. Self-enclosing borrow result. Result local? No. What's it saying? Yeah, up value doesn't exist. Method not found. So enclosing, okay, I'm obviously missing a level of induction here. Enclosing contains an optional compile result. Oh, I have to unwrap it. Right? Yeah. And then this doesn't like the fact that I'm doing an OK here. This expression is an option U8. Oh, option U8. Yeah, and now we just, okay, now we're just missing add up value. All right, very good. Wow, that's kind of annoyingly boring. All right, not boring. Why did I say boring? Long, annoyingly long. So we call this after failing to resolve a local variable in the current function's scope. So where are we calling this? Oh, we don't have it yet. Did I miss it? Nope. Okay, we're going to do that. We're getting there. So we know the variable isn't in the current compiler, which I'm calling compile results here. Recall the compiler stores a pointer to the compiler for the enclosing function. Okay, that's what we just refactored. And these pointers form a linked chain that goes all the way to the root compiler for the top-level code. Thus, if the enclosing compiler is null, we know that we've reached the outermost function without finding a local variable. The variable must be global, so we return -1. It might end up being an entirely undefined variable and not even global, but in locks we don't detect that error until runtime, so from the compiler's perspective, it's hopefully global. Otherwise, we try to resolve the identifier as a local variable in the enclosing compiler. In other words, we look for it right outside the current function. For example, this. When compiling the identifier expression at 1, resolve up value looks for a local variable to x declared in outer. If found, like it is in this example, then we successfully resolve the variable. We create an up value so that the inner function can access the variable right through that. The up value is created here. Here's add up value. So we're getting the up value count. In our compiler, we have an up values array that contains an isLocal and an index. So this is the isLocal, true, and the index is whatever the depth is that we got back from. Really? It's whatever we got back from resolve local, right? Resolve local returns the depth of the enclosing variable's name. Okay. The compiler keeps an array of up value structures to track the closed over identifiers that it has resolved in the body of each function. Remember how the compiler's local array mirrors the stack slot indexes where the locals live at runtime? This new up value array works the same way. The indexes in the compiler's array match the indexes where the up values will live in the object closure at runtime. Okay. So we're just creating a mirror of what's going to happen at runtime. And because now we need this thing here, we need up values, which is going to be a vec of whatever the hell these things are. isLocal and index. It's just a tuple of isLocal, which would be a Boolean, and an index, which is U8. And is that all we're talking about here? Or should I just make it a name struct? Should I create an up value struct, up value? bool. Oh, got it backwards. Is local bool and index of U8. Should I do it this way? Sure, why not? And then I want to derive default on it. Do I need to, or just the vec? Zero size vec. Okay, yeah. So it's just one error so far. We haven't got to the point where we have. Oh wait. So add up value needs to return. This needs to be an OK, right? Of this. Let me just stub out add up value. It takes a self, a depth, or index, I guess, and is local. And I'm just going to stub it out with, and it returns a U8, and it's going to return 0 for now. And let's see if we have any lifetime issues. Expected enum of option. Oh, this should be of option U8, sum. Go away. Okay, we have 8 warnings. Oh, field is never read, resolve up value is never called, add up value is never, okay. Yeah, okay, we're good, we're good. Okay, so we don't have any lifetime issues, we just have unused issues, which we're gonna fix soon. Hopefully I can get through this section before I have to stop. All right, so what add up value does is it just pushes onto the array this struct, and it returns how the index of that entry. So let count equals self dot up values dot. Oh, this is going to have to be in an RC. Borrow. I mean a ref cell len. So let's fix that now before we get any further. Here. And then that's going to be the count. We're going to say self.upvalues.borrow mute dot push up value of index and is local. Right, and then we're going to return count. I guess we're going to do overflow detection somehow at some point. Ooh, didn't like that. Expected U8 as U8. Done. Okay, now we're down to 6 warnings. So I think that's all we need to do for add up value, right? The compiler keeps an array of up value structures to track the closed over identifiers that it has resolved in the body of each function. Remember how the compiler's local array mirrors the stack slot and indexes with locals over runtime? Oh, I already read this. This function adds a new up value to that array. It also keeps track of the number of up value the function uses. It stores the count directly in object function itself because we also need that number for use at runtime. Oh, so we're going to have to add this to the function. I missed that. When do we add that? Did I just gloss right over that, or is that to come? Here. We're going to add up value count. Okay, so let's get there in a second. But what that means is we need to actually pass it in down here. Result dot up values dot borrow dot. Yep, borrow dot len. Right, so when we create a new function, we're going to have to pass in the number of up values we have for that function. We don't care about the actual value. We just care about how many there are for the function. All right, we'll get there. This function adds a new, all right, keep track, right? Like constants and functionality, the up value count is another one of those little pieces of data that form a bridge between the compiler and the runtime. The index field tracks the closed over variable slot index. That way the compiler knows which variable in the enclosing function needs to be captured. We'll circle back to what isLocal field is before too long, Finally, add up value returns the index of the created up value in the function's up value list. That index becomes the operand to the op get up value and op set up value instruction. All right. There. That's the basic idea for resolving up values, but the function isn't fully baked. A closure may reference the same variable in a surrounding function multiple times. In that case, we don't want to waste time in memory creating a separate up value for each identifier expression. To fix that, before we add a new up value, we first check to see if the function already has an up value that closes over that variable. And then we return the index of that. So, let's just fix this real quick here. I'm going to throw it in here now because why not? Up value count. Size. I got an extra space in there, but I don't care. Format will fix that. Up value count. Size. Up value count. Up value count. Self up value count. What's this? Oh, we need to create a default up value count of 0. Okay. So that's fixed. So now let's take a look at, let's take a look at this. This is an add up value. Before we do this, we're going to look. We're going to say self up values, borrow, iter, vec, iter, find position. Okay. So we're going to say let up value equals up value index is local. We're going to say position, and this returns an option. So if let sum pos equals position of x where x is equal to up value, then we're going to say return pos. Otherwise, we're going to do this business here, and we don't need to create it again. We can just say up value and move it over. Right? He says questioningly. Nope. Oh, do I put the ampersand here? Nope. Do I do this? Nope. Okay. Now I'll actually look at what the error says. Expected U8. Oh, I have to say U8 as U8. Okay. What should this be? This is an ampersand up value, and this is an up value. So if I just say I thought I had this. Oh, I can't compare up value. Derive partial EQ. Yeah, okay. We're down to 3 errors. Resolve up value is still not called, and add up value isn't called because resolve up value is never called. Okay. At some point we have to call resolve up value. I assume we're getting there. All right. So this is essentially this code here. I'm using this iterator to get the position of this particular item. If we get a sum, then we know we found it and we can return it. Otherwise, we'll just insert the new one and return the count that it was here, because that's the index of it. Okay. And this is always true for now, but I guess we'll get to a false at some point. And whenever this happens, I always feel like switching this, refactoring it to an actual textual words instead, like I did with a chunk. Just as an example, when we're printing out this jump style, it's either a forward jump or, oh, I should rename that. Okay, I'll rename that later. This shouldn't be forward jump. This should just be jump. And we can see jump style forwards or backwards. In the book, this was a Boolean to say whether it's forwards or backwards. But it's more maintainable if you can actually see the words here. But for now, we'll leave that like that. So I did this already. These two functions access and modify a bunch of new states, so let's define that. So we have the up value count. I added that to function. Initialize it to 0. I did that. And in the compiler, we add a field for the up value array. I did that. It's a vec. For simplicity, I gave it a fixed size. The up value and upset up value instructions encode an up value index using a single byte operand. So there's a restriction on how many up values a function can have, how many unique variables it can close over. Given that, we can afford a static array that large. Sure. Although I'm just using a vec. Maybe I should do with capacity on it. We also need to make sure the compiler doesn't overflow that limit. Oh, right. Yep. I knew we were getting there. So if, I guess we can call this up value count. Stop it. If up value count is equal to uint8 count, 255. This needs to return an error. Return error. And we're going to have to refactor everything now. Find results. Too many variables. And that's a brand new one. Otherwise we return OK of this. So now this becomes a result of u8 or a find result. Which means that this resolve up value, when it calls add up value, needs to question mark that out to get the find result, and then resolve local. Oh. Am I still missing where this is called? Okay, let's say resolve up value. Ah, it's here. So we haven't gotten there yet. Okay. So resolve up value is going to return a find result of too many variables. And let's see, where is my... Here it is, find result. So we can just throw it here, too many variables. And this is going to blow up. No. Oh, yes, it does. It doesn't like that. Oh, because this needs to be an OK result. And what's this? Oh, this is saying that we don't know. Okay. So find variable is going to return a find result. If we'll say let find result is equal to this thing here, and then we can say match find result of this, and it's either uninitialized or find result too many variables. It becomes an error of find result. Not found, it's none. If it's depth of something, then we get this, we pass in the depth. Okay. All right, that works. And the errors are too many variables aren't, because these two aren't. Okay, very good. Here's the up value struct, and I already did that. The index field stores which local slot the up value is capturing. The isLocal field deserves its own section, which we'll get to next. Flattening up values. Okay, this compiles. But right, we're not using resolve up value yet. Okay. I have about 20 minutes. Is that going to be enough time to do all? Oh my God. Okay. Let's see how far we can get. In the example I showed before, the closure is accessing a variable declared in the immediately enclosing function. Locks also supports accessing local variables declared in any enclosing scope, as in this. Right, here we're accessing x in inner. That variable is defined not in middle, but all the way out in outer. We need to handle cases like this too. You might think this isn't much harder since the variable will simply be somewhere farther down on the stack, but to consider this devious example. Mid calls outer, outer creates this and returns middle. Middle creates another function. Okay. When you run this, it should print create from outer, create inner struct. Come on. Sometimes problem using the trackpad is you run out of space on the trackpad when you're trying to select something. Okay, so we're going to call this devious. Because they say it says devious example, we're going to call it devious example AST, and we're going to call it devious. Right, return from outer, create inner closure, and then value. And that's what that guy does. I know it's convoluted. The most important part is that outer, where X is declared, right there, returns and pops all of its variables off the stack before the declaration of inner executes. So at the point in time that we create a closure for inner, X is already off the stack, right? So this is what they were talking about before, where things can move off the stack before you can refer to them, so you have to be aware of that. And this, I try to set out the execution flow for you. See how X is popped? 1. Here it is. Before it is captured, 2. And later accessed, 3. We really have 2 problems. We need to resolve local variables that are declared in surrounding functions beyond the immediately enclosing one. We need to be able to capture variables that have already left the stack. So if I run this with the current code, cargo run, yeah, return from outer, create from inner, and then undefined variable X. So we're 2/3 of the way there. Return from outer, create inner closure, and then this prints value. Fortunately, we're in the middle of adding up values to the VM, and up values are explicitly designed for tracking variables that have escaped the stack. So in a clever bit of self-reference, we can use up values to allow up values to capture variables declared outside of the immediately surrounding function. The solution is to allow the closure to capture either a local variable or an existing up value in the immediately enclosing function. If a deeply nested function references a local variable declared several hops away, we'll thread it through all of the intermediate functions by having each function capture an up value for the next function to grab. So how we do that? In the above example, middle captures the local variable X in the immediately enclosing function outer and stores its own up value. It does this even though middle itself doesn't reference X. Then when the declaration of inner executes, its closure grabs the up value from the obj closure for middle that it captured. That captured X. Function captures either local or up value only from the immediately surrounding function, which is guaranteed to still be around at the point that the inner function declaration executes. In order to implement this, the resolve up value becomes recursive. Where do we actually start the whole problem? I'm looking right down here. This is one more reference to it. Where do we call it? Oh, I missed this. This is the very first. Okay. All right, let's do that. It's going nuts here. Okay, so this is a named variable. Or aimed, as I call it. So we're going to say if... Right now it says if resolve local, then get the locals. I guess we could say else if let some up value arg equals self resolve up value. Oh, except we're not going to do that. We're going to call self result borrow resolve up value. But that does not give us an option U8 back. So fn resolve up value, self name, token, option U8, match, self, result, borrow, resolve up value name. Oh, and this is where we get too many, right? Error. Find results uninitialized. Oh, I guess we don't care about that, right? Too many variables. I forget what the error message was now, but I'll put it here, self error to do error message. And I'll scan down for it if I remember. And it returns none. If it's an OK val, then we return the val. If it's anything else, we're going to panic. Invalid. Return from resolve up value. And that'll be that. And then we can just say here, self resolve up value of name. Then it'll be up value arg, opcode get up value, or opcode set up value. Okay, so I think that's what this is doing here. Oop, I forgot how to spell the word let. There. Capital T for token. All right. Okay, and that resolved all that. Okay. So where were we? Right. So we were in resolve up value, and we need, after this, we have to do a recursive call. All right. So this is this part here. This is resolve local. If local is not one, then we're going to say let up value is equal to self enclosing. Right, I'm looking here and see that we're calling the enclosing version of up value. Borrow, resolve up value, name. And then I guess we could match on that, right? If it's none, okay, none. I guess we question mark it, just like we did the other one, right? And if it's some, then we're going to add comma, sum depth, return, okay, sum, self, add up value, depth, and now it's false. I guess with this one, we don't have to worry about the returns because the match can just do the return, right? That does not compile. Self-enclosing borrow resolve up value. Method not found. Oh, I have to unwrap it, right? Because it could be it could have been a none, but we know it's not a none now. So we have to do the as ref borrow, unwrap. Two warnings. Unreachable expression. Oh. Oh. Yeah, so we don't actually want to do it like this, right? Because if it's none, we want to keep looking. Duh. So we can say if let sum depth equals this business, then we can return that. Otherwise, we'll do this. Yeah. Okay, so this is doing this, right? If local is not 1, right, if it has some depth, then we're going to add the up value and return an OK of an option U8. Otherwise, we're going to call this resolve up value on the enclosing, which could get recursive, right, because it could end up calling resolve up value of the enclosing and keep working its way up. It's only another 3 lines of code, but I found this function really challenging to get right the first time. This is in spite of the fact that I wasn't inventing anything new, just porting the concept over from Lua. Most recursive functions either do all the work before the recursive call, a pre-order traversal, or on the way down, Or they do all the work after the recursive call, a post-order traversal, or on the way back up. This function does both. The recursive call is right in the middle. Here, I guess, and then we have a none, I guess. We'll walk through it slowly. First, we look for a matching local variable in the enclosing function. That's here. If we find one, we capture that local and return. That's the base case. Otherwise, we look for a local variable beyond the immediately enclosing function. We do that by recursively calling resolve upValue on the enclosing compiler, not the current one. On the enclosing compiler, not the current one. This series of resolve upValue calls works its way along the chain of nested compilers until it hits one of the base cases. Either it finds an actual local variable to capture, or it runs out of compilers. The other base case, of course, is if there's no enclosing function. In that case, the variable can't be resolved lexically. That's here. And is treated as a global. When a local variable is found, the most deeply nested call to resolve upValue captures it and returns the upValue index. That returns to the next call for the inner function declaration, right? So that would be here, right? We add the upValue here with a true, and then the remaining ones are going to add false, I guess, for the not is local. As each nested call to resolve upValue returns, we drill back down into the innermost function declaration where the identifier we're resolving appears. At each step along the way, we add an upValue to the intervening function and pass along the resulting upValue index down to the next call. Each recursive call to resolve upValue walks out one level of function nesting. So an inner recursive call refers to the outer nested declaration. The innermost recursive call to resolve upValue that finds the local variable will be for the outermost function, just inside the enclosing function where that variable is actually declared. Yeah, I think I get it. I think I get it. Right? Resolve upValue can't find it, so it recurses, found it here, it adds it to, and calls add upValue, returns it. Now it says, okay, now I found an upValue here, so we capture it and return it. Note that the new call to add upValue passes false for isLocal. Now you can see that flag controls whether the closure captures the local variable or an upValue from the surrounding function. By the time the compiler reaches the end of the function declaration, every variable reference has been resolved as either a local, an upValue, or a global. Each upValue may in turn capture a local variable from the surrounding function, or an upValue in the case of transitive closures. We finally have enough data to emit bytecode, which creates a closure at runtime that captures all the correct variables. So now, if I look at function, so after we emit the closure, which is all the way down here, we're going to loop over for each upValue count. We're going to emit either a 0 or 1 byte for the isLocal, and then an index. Okay, so we can just do that using result.upvalues.borrow upValue in iter. Right? And then we have an upValue. We can say self emit byte upValue that is local. Except in locks we do it this way, and then it's if it's true, then it's 1, else it's 0. And then self emit byte upValue dot index. Yeah, okay, that compiles. The upClosure instruction is unique in that it has a variably sized encoding. For each upValue the closure captures, there are 2 single byte operands. Each pair of operands specifies what the upValue captures. If the first byte is 1, it captures a local variable in the closing function. If 0, it captures one of the function's upValues. The next byte is the local slot or upValue index to capture. This odd encoding means we need some bespoke support in the disassembly code for upClosure. Oh, right. We need to pass in the upValue count. Did I do that? I did, right here. So, right. So now in our function, let's go over to the disassembler. How are we doing on time? Ooh, running out of time. All right, here's our disassembler. We need to get the function. So after we do the new line, I need to extract the function from the constants table. If let value func f, I guess function, sure, is equal to self to constants. Ooh, how do I extract it? It's value, right? Value array. It's just a vec of values, but it's private. Can I pull one out? Ooh, I guess I can delete this old code here. Read value. There we go. Read value of constant as usize. Okay. So now that we've read the value, we can say function.upvalue, right? So we can say for I in, or they have j. All right, so let's use j in 0 dot dot function dot upvalue count, which I'm probably not allowed to do because it's not pub. And then we're going to just read the chunks. Okay, so we're going to say let is local equals self dot code of index plus equals 1. Let, oh, I can't use index. I guess we can say I guess we'll use I, because I want to use index for the other thing. Right? You want to say let index equals self code of I, and then I plus equals 1, and we have to change this to I. And then this is going to be else panic. Oh, this should be a closure, right? Oh no, that's the opcode is closure. Okay, no function at position constant. I'll do that for now, and if we actually hit that error, we can debug it further. All right, so now we're going to say print ln, so offset -2, so 0, 4, and then we have a few spaces. Let me just copy. I don't know how many spaces these are, so I'm just going to copy all that, paste it there. We're going to put the string there, and then the number, which is the index. Oh, we can just put, we can say if self code equals 0, then it's up value, else local, right? And then I can just put here, I can say is local, oh, I missed the quote, and then index, just like that. Does that look right? That looks right. Okay, does it compile? It does not. Oh, this is the index, offset -2. And this has to be I also. Yeah, and we can't access up value counts. So let's go to function. Got to bounce all the way over here and add a new getter, hub fun, up values, self, resize, self up value count. And then just call this up values. Go away. Okay, and the warning is J. Oh, we don't need a loop variable. All right. Okay. All right, so that compiles. For example, take this script. Sample. If we disassemble the instruction that creates the closure for inner, it prints this. Okay, let's see if that's true. Cargo run sample less. Oh, I forgot the space again. Let me fix that real quick. Because it's bothering me. There should be a space right here. Okay. Let's try again. Okay. So 9 op closure, fn inner, up value 0, local 1, up value 1, local 2. Okay. So I think it's working. With that, our compiler is where we want it. All right, these both have a single byte operand, so there's nothing exciting going on. We do need to add an include so the bug module can get to as function. Okay, I'm not worried about the include statements because this is not C code. So we can see these closure statements. We do see a get up value. Here, I guess we're not doing any set up values. It's not actually running yet because I don't see any output. It's supposed to print, isn't it? Yeah, it's supposed to print this. Oh, we're never calling it. I don't want to try calling it because it's probably going to break. But we're at a good point right now where we can... where we can actually push this, and I'm out of time. So git status, git add source, git commit -m section 25.2, and this is called up values. That's all it is, up values. All right, and we'll push it up, and we're going to call it a stream. Here we go. So this is all we did. That's right. We started off by fixing a bug. We did 25.1 closure objects and 25.2 up values. That was intense. That was pretty intense. Meanwhile, back at the farm, let's go visit Togglebit. So let me pause my music, see how Toggle's doing, and I will see. Let's see. Let me pull him up. There we go. And I will, I'll see you tomorrow with section 25.3. Right? Where's 25.3? And it is called up value objects. I'm just going to, just for fun, sample. Let me try calling outer and see what breaks. It didn't do anything, so there's more work to do, I guess. Yeah, it's time to hop over to the VM to get things running. Okay, so we're gonna do that tomorrow. That should be fun. All right, so thank you everyone for hanging out with me. I really appreciate, and I will see you tomorrow with more crafting interpreters. Take care.